Hi, I'm Alvin, a PhD candidate with the Edinburgh Centre for Robotics. I'll be presenting our work titled Practical Feature Selection for Online Reinforcement Learning and Planning in Relational MDPs. This is a joint work with Dr. Petrick. In our work, we are interested in symbolic planning problems where agents reason over task-level actions to achieve goals. For example, in our paper, we propose two domains. First, robot inspection, where a robot is tasked to inspect objects and transmit the information back to the human. In the second domain, the robot is tasked to pick up objects and bring it to its goal location. In applications where the model is not known, we can use reinforcement learning, where the agent acquires experiences to improve its policy. Reinforcement learning algorithms are characterized by sample and computational complexities. In our work, we investigate methods to improve upon these complexities. A second motivation is that we want policies that have been learned to be able to generalize across different planning problems of the same domain. This is typically difficult for symbolic planning problems where the model is unknown. To learn the policy, we use model-free reinforcement learning to learn the Q function, which maximizes the finite horizon expected return. We use Q lambda with the TD error as defined in equation 3. As we are interested in large-scale planning problems, we need to approximate the Q function. We chose linear function approximation as it has strong theoretical convergence guarantees. The parameterized Q function is then given as a dot product of the feature vector and the weight vector. We want to learn the features and weights in an online manner. Therefore, we adopt IFDD+. IFDD+ requires an initial set of features to be given. These are added into the feature set F. Next, it generates candidate features, which are conjunction of pairwise features in F. At every step, as the agent executes an action, it receives some experience and the TD error is computed. The TD error is then added into the relevance of active candidate features. As the relevance are accumulated, candidate features with relevance exceeding a threshold xi are added into the feature set F. This in turn generates even more candidate features, which are increasingly complex. We identify two aspects of IFDD+ that can be improved in our work. First, xi is domain dependent and depends on the nature of the reward function. Therefore, it is difficult to fine-tune and it has to be fine-tuned for each specific planning problem. We propose a domain-dependent independent parameter kappa, which represents the maximum number of features that can be added in at any step. So if the number of candidate features that is to be added in exceeds kappa, we only add in features with the highest number, with the highest relevance, and reject the rest. We then increase xi to the maximum relevance of the rejected features. In essence, we increase xi when there are too many features to be added in. We assume that that happens when the experience are inadequate and there are way too many unnecessary features that are being added in. The second aspect is the IFDD+ requires an initial set of features. This can be the set of every single state fluent. However, some of them could be unnecessary to estimate the Q value of an action. Therefore, we propose a model-based method where we look at a 2x slice dBn representing the transition function. The features of an action are then its D neighbors. If D is equal to 2, then the features are the neighbors and the neighbors of the neighbors. While our method requires the arcs in the dBn to be known, it does not require knowledge of the exact nature of the relation or the transition probability. Therefore, our method is less reliant on the model accuracy. The third contribution of work is the introduction of lifted features to represent the Q function. The features are no longer grounded state fluents, but rather lifted state fluents. And we are learning the features and weights for lifted action fluents rather than for every single grounded instantiation of the action fluents. This gives us three advantages. First, better scalability as the number of fluents, the number of lifted fluents does not increase with the number of objects in the planning problem. The second advantage is that it gives better generalization as we consider grounded instantiations of every of a lifted action fluent having the same shattered features and weights. Therefore, when we acquire experience of a particular grounded action, we are updating the knowledge of every other grounded instantiations of the same lifted action. The third advantage is that the Q function no longer depends on the objects of the planning problem, but rather on lifted fluents. Therefore, this Q function can give us a policy that can be applied to a different planning problem with different number of objects. We covered a short example over here. For further details, please look at our paper. So we have a particular action called inspect object, and it has these parameters that are in red. So these variables in red can be grounded depending on which grounded instantiation for inspect object we are looking at. For example, if we are looking at R1 and object 1, then we can just replace the variables accordingly. However, you could see that in this set of listed features, there are still some variables in blue, which are not part of the parameters of inspect object. So these variables in blue, we refer to them as free variables, and we need to find a way to substitute them as we need to ground the listed features in order to determine the Q value. So the grounding of the listed features are important as affects the Q values and the online feature selection. We propose two considerations to select a substitution. First, we select a substitution that maximizes the Q value. This is similar in spirit to optimistic Q learning. The second criteria is that we could select a substitution that maximizes the number of active features. We run some simulated experiments using RDDL sim as a simulator. So we have two set of experiments. First, for the grounded features, we are benchmarking against the vanilla IFDD+, which is the green plot, and the results shows that our proposed methods outperform the benchmark. In the second set of experiments, we consider lifted features for the Q function approximation. Every single episode is a randomized planning problem, and so the feature vector and the weight vector is transferred from one episode to the next for a different planning problem. And results shows that it does generalize well to different planning problems, as you could see that the number of goals increases over episodes, as well as the rewards increase over episodes as well. In conclusion, we propose a model-based feature selection method to improve sample complexity. We also propose lifted features for generalization over different planning problems of the same domain. For future work, we could like to combine a structured learning algorithm with our model-based feature selection. We could also like to look at a more principled method to ground the free variables in lifted features. Thank you for your time.